this link work this time, everybody?
Yeah.
All right, great. Well, it looks like it's time to start for those of you who are in attendance. Are there any homework questions we should review before we get started?
Ew.
I hear a yes. All right, let me get my book out here. And let me get a piece of paper out here. Which questions do we need to look at? Which questions do we need to look at? Who asked for a question? Somebody asked for a question.
I have a question on number
Sure,
49 for 2.1.
2.149. Any others? No others, just 2.149. That's it. All right, that works for me. Let me find it here. Why can't I find it? 2, 2, 2. Two 149. Let me make sure that's it. Yeah, that looks like that's it. Is that the 3x squared minus 8x plus 7?
Yeah.
And let me get the wording of that. Two, 4, 9 says solve each quadratic using the quadratic formula. Okay, so x equals minus b plus or minus b squared minus 4ac all over 2a. And we are given 3x squared. And I'm going to bring everything over to the left side. Minus 8x plus 7, and we'll set that equal to 0. That makes sense?
Yeah.
A equals 3, negative 8, c equals 7. So x equals minus b, which would be 8 plus or minus the root of b squared, which is 64, minus 4 times 3 times 7 all over 2 times 3, which is 6. So x equals 8 plus or minus the root of all this over 6. Let's get out our calculator here. And we want 64 minus 4 times 3 is 12 times 7. So it looks like it's negative 20. Is that what you got?
Yeah, so far.
Okay, so far so good. So we want to take this and factor it and see if we can get something that has a square root. And we know that 20 has factors of 4 and 5, and we can take the root of 4. So we could say that looks the same as 8 plus or minus all over 6 root 4 root 5. And that's negative, isn't it? So that's 4, let's say negative 5. So x equals 8 plus or minus root 4 is 2, root negative 5 all over 6. And before we take on that, we'll divide everything by 2. And that should give us 4 plus or minus root negative 5 and divide 6 by 2. And we get 3. You agree with that?
How'd you get the 3 again? Like over 3.
Well, I had 6 in the denominator, 8 in the numerator, 2 in the numerator, so I divide everything by 2.
Oh, okay.
So
Got it.
8 over 2 is 4, 2 over 2 is 1, 6 over 2 is 3. Now I just have to resolve this root -5 business. So we okay here so far?
Yeah, I understand so far.
Okay, x equals 4, and I'm going to separate these out. That's 4 over 3 plus or minus. Now this root -5, that's really the root -1 times the root 5, isn't it? Which is I root 5. Root of -1 is I, isn't it? So that's I root 5 over 3. Okay so far?
So you just divide both them by 3? Yeah, basically.
Yes, I just took the 4. This looks like A plus B over C, which looks like A over C plus B over C. If we were to given two fractions like this and asked to combine them, we would say, well, we need a common denominator. Well, we have it at C. So if we have a common denominator, we just add the numerators, A plus B. So we just went the other direction. Just took A over C and B over C. Okay, makes sense?
Yeah, thank you.
All right, and now do we need to go any further, or are you okay with this?
I think that's what the answer said when I checked it.
Okay. Now you could write it out as 4 over 3 plus root 5 over 3i. That would be one solution. And we could also have 4 over 3 minus root 5 over 3i. So we could have a solution set. We could list this way as well. Either way would work. Okay, any other questions on previous homework before we do today's work? The plan today is to cover sections 2.4, 2.5, and 2.6. And again, if there are any questions on previous work, 2.1, 2.2, 2.3, we'll take those. We still haven't had everybody complete the test, so I'm not going to review the test yet. Still got people that, for some reason, were unable to take the test. Okay, so let's take a look at what we're going to do today. One thing I want to remind you of is when you're submitting your homework, please be sure that in the upper right-hand corner on each page you turn in order to get credit, you're going to want to have your first and last name printed so I can read it. Tell me how many pages you're sending me and which page this is. If this is page 1 of 3 pages, and the next one is 2 of 3 pages, the next one is 3 of 3 pages, so I know how many to look for to make sure you get credit. And then this is Math 141, and I have more than one section. So please put your section number, which is 3737, and then put the date that you're turning in your homework, month, day, year, and then what assignment homework this is, what sections. If it's section 2.1, 2.2, 2.3, put that there so I know what I'm looking for. And then on the subject line for an email that you're sending me, be sure that you list what homework assignments you're turning in to make sure I get everything that you're turning in. Otherwise, I won't know what it is you think you're sending me. Sometimes people tell me they're going to send me section 2.1 and they don't send me 2.1. They might send me 1.9 or something, who knows. So make sure you tell me what you think you're sending me so that when I do a check of your work, that there'll be an agreement. Okay, questions on that part of it at all, on what we want the homework to look like?
Yeah, so quick question. So for the page number, I see you have returned all three pages, like 1 out of 3, 2 out of 3. So do we have
Yes.
to do that on each single page, or like if it's the first page, I just write 1 out of 3, and then on the second page I write 2 out of 3, like that?
Yes, and on the third page, you write 3 out of 3.
Okay.
So I know how many pages you're sending me, which is the 3, and which page this is of the 3. I'm looking at page 1 of 3, On the next page, I'm looking at 2 of 3. The next page, I'm looking at page 3 of 3. That way I know that I'm seeing all your work.
Okay, thank you.
Sure. Other questions? Okay, now I put that in there because we're getting people that are sending it in. This is the 6th week or the 7th week, whatever it is. I guess it's the 7th week. And we're still getting people that are not labeling their homework properly, which means you may not be getting proper credit for your homework. So please follow this format when you turn it in. Okay, section 2.4 talks about dividing polynomials, and we are going to take a look at the remainder and factor theorem. And let's just take a look at some of the objectives we're going to be doing on this one. So the objectives on 2.4 are going to be, we want to be able to use long division to divide polynomials. So I'll just put a divide sign here. We want to use long division to divide polynomials. We also want to be able to use something called synthetic division to divide polynomials. We're going to evaluate using the remainder theorem, and we'll talk about what that means. And we're also going to use something called the factor theorem. So those are the things that we want to be able to do as a result of going through today's lesson. Now, when we're doing division, when we're doing long division, I think you first went through this probably in the 4th grade when maybe your teacher said, you know, if I want to divide 833 by 49, here's how I would do that. And I'll take 49 and divide it into 833, and then I may have decimals. I don't know if I do or not. And I'll say, well, let's see, will 49 go into 8? We say, no, 49 is bigger than 8. Well, will 49 go into 83? We'll take the next digit over. Well, yes, 49 will go into 83 because it's smaller, but it won't go in twice because twice would be bigger than 83. So we'll say it'll go in once, and I'll put a 49 down here. Now I'm going through this exercise using what you've already learned because we're going to use the same approach when we divide polynomials. We divide a trinomial by a binomial, for instance. We're going to use the same approach. So we do 1 times 49, we get 49, and then we're going to subtract. So I'm going to say, okay, I'm going to change the sign and do a subtract. So 9 from 13 is 4. We take out that, make it a 7. 4 from 7 is 3. And then the next step is bring down this 3, isn't it? And then repeat. 49 into 34. Well, that's 49 won't go into 34, but it'll go into 343. And it turns out it'll go in there 7 times. 7 times 9 is 63. Carrier 6, 28, 6 is 34. And then subtract. 343 from 343 leaves a remainder of 0. So our answer is 17. So that's the long division process. In case it's been a number of years since you've done it. That's how we do it. If we ended up with the remainder down here, because these values were different, then we would say plus the remainder. And remember, the remainder is a fraction of this value here. So if we had a remainder of 2, then we would say 17 plus remainder of 2 over that value there, if we had a remainder. We don't in this case, but if we did. So then our answer would be this value here plus the remainder, which is this value over this value. So with that in mind, then let's take an actual value then that we're divide. Let's say you're given x squared. Well, before I do that, let me just stop. Everybody okay on this? Any questions on what we did there? Okay, so let's take x squared plus 14x plus 45. And let's say we're going to divide that by the binomial x plus 5.
Could you move the paper down just a little?
Oh, yes. Yes, I will. No, I don't want to divide by that. Let's see, I want to divide it by x plus 9. Okay, let me just move this back a little bit so that we can see everything here. Okay, so I'm going to divide the binomial x plus 9 into, and let me just move this down a little bit, into x squared plus 14x plus 45. All right, and we'll use the same kind of approach. So if I divide x into x squared, I'll take the first term here, divide it into the first term here. So x goes into x squared, x times x is x squared. That's what we would expect to see, isn't it? Then x times 9 gives me a plus 9x. So now we see if we divide x into x squared and we have a binomial here, we take that x times both terms in the binomial, x squared plus 9x. And then we subtract. So I change my signs. And when I do it, I put a circle around the sign that I've changed so I know what it is I'm doing instead of just trying to remember. So x squared minus x squared, those are going to cancel. And 14 minus 9, that's going to be 5, and it's going to be positive because 14 is larger. So it gives me a 5x. And then the next step is to bring down the 45. And then repeat. So x goes into 5x, positive 5 times x, 5x, 5 times 9, positive 45, and then subtract. Change my signs, combine terms, the 5's x's cancel, 45's cancel, my remainder is 0. So my solution is x plus 5. Okay, that's what I get when I divide the trinomial x squared plus 14x plus 45 divided by the binomial x plus 9. Questions at this point on what we did there? So that says that x plus 9 times x plus 5 equals x squared plus 14x plus 45. These are the factors, aren't they, of that trinomial? Okay. All right. Let's try another one then. Let's say we want to divide. You might see it in a format that looks like this. 7 minus 11x minus 3x square plus, let's say, 2x cubed. And we want to divide that by x minus 3. So one of the first things we want to do here, 1, 2, 3, we've got 4 terms here for this polynomial. We want to arrange these in descending order of exponents, so that when we rearrange it, we'll get 2x cubed minus 3x squared minus 11x and positive 7. And we're going to divide that by x minus 3. Okay, so again, we'll take x into 2x cubed. So it's going to be a 2. And we have x cubed So we need an x squared here, don't we? Because when we multiply this times this, we have to get this value. So we get 2x cubed when we multiply this value by this value, the first one. And then multiplying by the second one, we're going to get a negative 6x squared. So 2x squared times negative 3. So then we subtract. So I change my signs and combine terms. So those are going to cancel. And I have 6x squared positive, 3x squared negative. So that leaves me 3x squared as a positive value. Bring down the next term, negative 11x, and repeat. X into 3x squared, that's going to be a 3x, isn't it? 3x times x is 3x squared. And 3x times negative 3. Okay, is that what we've got here? 3x times negative 3. That's going to give me positive 9x. And I'll change the sign here. Change the sign here. Those will cancel. And now I've got negative, let's see, I guess that should have been a negative 9, shouldn't it? I'm going to be careful here. That was a negative. Positive times a negative is a negative. This guy here. So we change the sign on that. And negative 11, positive 9 is a negative 2 x's. And bring down the next term, which is a 7. Divide again. X into negative 2x is going to give me a negative 2. Negative 2x. Negative times a negative is a positive. 3 times 2 is 6. Change my signs because I'm subtracting. Those cancel. Positive 7, negative 6. So my remainder is 1. So now my solution, which I show here, is going to be 2x squared plus 3x minus 2 plus the remainder, which is 1 over the divisor, x minus 3. Okay, so my solution then looks like this. 2x
Could
squared.
you explain how you you change the signs from adding to subtraction again?
It's because I'm subtracting.
Oh, okay.
If I have 4 and I bring down a 2 and I want to subtract this 2, I have to change that sign to a 2 because I'm subtracting. Now I combine them and I get 2.
So if you change that one sign, you got to change the rest of the equation too.
Yes, whatever I'm subtracting.
Oh, okay.
Anything I'm subtracting, I change the sign
Okay.
because I'm subtracting this whole value. If I have 2x cubed minus 3x squared, and below that I have 2x cubed minus 6x, and I say subtract this value from that value, then I'm going to have to distribute this negative, aren't I? So the negative goes here.
Yeah, you're right. Right.
And the negative goes here.
Okay, thank you.
And then when I combine, they cancel.
All right, got it. Thank you.
Yeah, it's just regular division, just like we've always done. This is what we've done for a long time. Other questions? Okay, let's see if I've got some other long division problems that I can work through. Yes, let me do that. Let me bring up. Okay, let's say I have, make sure I get a different one here. Let's say I have 3x squared cubed. No, let's make it 3x cubed. Make it more interesting. 3x cubed plus 4x squared minus 5x plus 3. And I want to divide this by x plus 4. Now you may not be given, you probably won't be given the problem in this format. You might just be given, here's a polynomial with a paren around it, and then the division sign, and then a binomial x plus 4. And you'll change that into this kind of a format so you can do the long division. So x goes into 3x cubed. Well, it's going to go 3x cubed, so I need an x squared here, don't I? So when I multiply what I have here for a quotient, I'll get 3x squared times x is x cubed. And then this quotient times the other term, 4. 4 times 3 is 12x squared. Now I'm going to change these signs because I'm going to subtract. I want to subtract this from this. This is a positive, so I want to subtract it, so I'll make it a negative. And this is a positive, I want to subtract it, so that's a negative. Now when I combine this positive and this negative, those cancel. When I combine this positive and this negative, well, 4 from 12 is 8. The type is x squared, and it's a negative because 12 is larger, isn't it? So I get negative x squared. Bring down my next term, which is negative 5x. And then repeat. X into negative 8x squared. Well, it's going to be negative. It's going to be 8. And it's going to be x, isn't it? Because when I multiply negative 8x times this, I get negative 8x squared. And then negative 8 times positive 4 gives me a negative 32x. Now I want to subtract this term, this binomial. So I'm going to change that to a positive and that to a positive and then combine. Those first terms cancel. Negative 32, positive 5. 5 from 32 is 27. The type is x, and it's a positive. Bring down the next value, which is a 3, and it's positive. And I divide x into 27x. Positive into a positive, that's positive. 27. So 27 times x, positive 27x, 4 times 27. Now let's see, 27 times 27 is 54, and double that, looks like I get 108. So I'm going to get positive 108. And then I'm going to subtract the second from the first. So I'm going to subtract it. So I'm going to mark that as a subtraction. And then when I combine these terms, those cancel. Negative 108 plus 3 is going to be negative 105. So this is my remainder. So then my solution is 3x squared minus 8x plus 27 plus my remainder. And my remainder is negative 105 over x plus 4. Okay, questions on that? So our solution then is shown here. Okay, questions? All right. Let's try one more. Do I have one more I can take you through? Let's try. I'll ask you guys to help me on this one. X plus 1 into 15x cubed, 14x squared, minus 3x minus 2. All right. When I divide x into 15x cubed, what do I get? Let's get some new volunteers. What do we get here when we do that divide?
15x squared.
15x squared. Well, okay, I'll give that a try. 15x squared times x gives me 15x cubed. Common base is x. Add 2 and 1, we get a 3. Plus 15x squared. And then we subtract. So we're going to change those signs to subtract. Those will cancel. 14 and 15. So we're going to get a negative x squared. Bring down the next term, which is negative 3x, and repeat. So x goes into negative x squared. How many times? Can we have a new volunteer so we can have everybody participating and having fun?
-1.
Negative 1. One like that.
Isn't it
Uh,
negative x?
It's x. Oh, it's x spot. My bad. -1x.
Negative 1
Negative
x.
x in general. Yeah.
You want it like that?
Negative x could be fine too, right?
Just negative x, right?
Yeah. Okay.
Just negative x. So let's try that. So negative x times x is negative x squared. Negative x times 1 is negative x. All right, so we've got that. We're going to subtract. So we change these signs. We combine. -3, +1. That's going to be a -2. Type is x. Bring down the -2. And then repeat. All right, new volunteer. When we divide x into this value, what do we get?
-2.
-2. -2 times x is -2x. -2 times 1 is -2. We're going to subtract this from this. So I'll change the signs and combine. That goes to 0 and that cancels. So our remainder is what?
0.
0. Okay. So we end up with a solution then that looks like 15x squared minus x minus 2. Okay, questions on what we did there? All right. Let's see here. What other concept do we want to make sure we go through? Let's take a look at another concept, which I'm going to call synthetic division. And let's try and do, let's see, let's take a problem we've done. Let's say we want to divide, which we've already done. We're going to do it in a different manner. We did x minus 3 into 2x cubed, 3x squared, 11x, 7. And remember what we got? 2x squared plus 3x minus 2 plus 1 over x minus 3. That's the solution that we got. Okay, now I'm going to do it. This was long division. Now I'm going to do it something called synthetic division. Now with synthetic division, we use just the constant that's multiplied by the variable. So we're going to take that coefficient and we're going to show it, right? Let's say we have a 2 here. Yeah, we're just going to use this coefficient. So 2 and bring down the 3, bring down the 11, bring down the 7, and we're going to divide that. So these are just coefficients. This is the coefficient of the x cubed type. This is the coefficient of the x squared type. I'm just putting these up there just so we'll remember what they are. And this is the x, and this was the x to the 1, and we can think of this as x to the 0, can't we? X to the 0 was 1. And then we're going to divide not by the factor. Keep in mind we're dividing by a factor here. So x minus 3 is a factor of this 2x cubed minus 3x squared minus 11x plus 7. And we multiply this times this, we'll get this. Here we're taking just the coefficients. Taking just the coefficients, and we're going to divide not by the factor, but by the x value. So if x minus 3 is a factor, remember that's where a factor is where it crosses. If we have a 0 remainder, that's where it crosses the x-axis. So the solution is that x equals 3. So if I divide this by 3, then the mechanics are as follows. I bring down this 2. Now these are just the mechanics of how synthetic division works. And then 2 times 3 is 6. And we combine these and we get -3. And we multiply here and we get -9. And we combine these and we get -20. Multiply here, we get -60. And combine these and we get -53. And these would be x squared. There'd be 2 of these. This would be x. This would be the constant x to the 0. And this would be our remainder here. So when we're doing synthetic division, we're taking just the coefficients. Now let me show you another version. If I divide x cubed minus 7x minus 6 by x plus 2, I can do that long division like we did above, or I could do it synthetically. Synthetically, I'm going to put just the coefficients here. So that's 1. Now you'll notice I don't have an x squared component here. I only have the x to the 1. So I have to put in a placeholder. So I'm going to put in 0. So this is the x cubed position. This is the x squared position. There's just a placeholder. -7 is the x of the first position. And then -6 is the constant. And if we're going to divide that by this factor, when we're doing synthetic division, we're going to divide then by -2, because x plus 2, setting that equal to 0 and solving for x, we get x equals -2. So here's the solution of x, here's the factor. So let's divide this -2 synthetically into these values here. So again, procedurally, we bring down the 1 and then multiply here. So we get a -2. Combine those, we get a -2. Multiply here, we get a +4. Combine these, we get a -3. Multiply here, we get a +6. Combine these, we get a 0. Here's our remainder of 0. Here our factors were, or our exponents were x cubed, x squared, x, and x to the 0. Here we're 1 less, aren't we? Because we're dividing by this value here. In factored form, that would be x plus 2. So these are all reduced by 1 exponent. So this would be 1 of the x squareds. This would be 2 of the x of the 1s. And this would be 3 of x to the 0s. So we have x squared minus 2x minus 3. And our remainder is 0. So x squared minus 2x minus 3. That's what we get when we divide this value by this value synthetically. Now I'm going to show you the same process, long division, and you tell me which one you think is easier. So let's put long division here. And let's divide x plus 2 into x cubed plus 0x squared minus 7x minus 6. So x goes into x cubed, x squared times, multiply back, x squared times x is x cubed. And this is 2x squared. And we subtract. Those cancel. And we get negative 2x squared. Bring down the next term. Do our division again. Positive, negative, so that's going to be negative. X into 2x squared is 2x. Do the multiply, and I get negative 2x squared minus 4x when I do the multiply by each of these terms in the binomial. And then I combine by subtracting. So this negative becomes a positive, this negative becomes a positive. Those cancel. Negative 7, positive 4 gives me negative 3x. Bring down my 6, negative 6, and repeat. X into negative 3x is a negative 3. 3 times x is negative 3x, negative 6. Change signs and combine 3x, those will cancel, 6x and 6. 6 and 6, those will cancel, so the remainder is 0. So my solution is shown here. So you can take a look. That's the same problem done synthetically up here and long division wise here. You're going to be asked to know both methods, but when synthetic division was introduced, the idea was, this makes long division easier. This makes the division of a trinomial by a binomial easier. We're taking just the coefficients and doing this method of division rather than having to go through the multiplying of all these exponents and keeping track of all the exponents. Okay, so that's the theory of it. Whether you think it's easier or not synthetically, the reason that it was devised is that it was supposed to make things easier. You guys have any comments on that, whether you think it makes it easier or not?
Wait, so for the synthetic, do you just like multiply all the coefficients by, for example, for your thing, -2? Is that what you did?
I did a division, didn't I? I'm dividing this into this. The process is to bring down the 1, multiply, and bring it over here and combine again. So the process is I bring down my 1, I multiply it by the divisor, which is -2, and I get that here. And then I combine these two.
Oh, wait, I didn't remember this. Yeah, my bad. Yeah, my bad. It's clicked into me now.
Okay.
Thank you.
-2 times -2 is +4. Combine to get -3 and so forth. Okay. Make sense to everybody? Okay, so we've covered long division and synthetic division. Let's see, is there something else that I should, well, let me just talk about, remainder theorem and factor theorem. Let's see if I've got an example or two I can step you through here. Theorem. Let's take a look at this one. If I'm given if I'm given 3x cubed plus 4x squared minus 5x plus 3, and I want to find f evaluated at -4, and if I use the remainder theorem, this says that x equals -4. So if I'm asked to find f at -4, I could just substitute, couldn't I? I could say f at -4, that's evaluating this at -4. So it'd be 3 times -4 cubed. plus 4 times negative 4 squared plus 5 times, no, negative 5 times negative 4 and plus 3. So 4 times 4 is 16 times 4 is 64 times 3. 64 and 64 is 128. 128, 64 turns out to be 192, doesn't it? And that's a negative. And then 4 times 4 is 16 times 4, that's a 64. And 5 times, that's a negative 5 times a negative 4, that's positive 20 and a positive 3. So when I combine all these values, I'll put that into my calculator, and I get negative 105. So that says F evaluated negative 4 equals 105. Okay, now if I were to use synthetic division to solve this problem, well, keep in mind what we're doing here. We're saying F evaluated at negative 4 isn't 0. That is to say, it doesn't cross the x-axis. It isn't 0. It's this far away from the x-axis, either positive or negative, in this case, negative. Now, what we can do is use synthetic division to verify what's going on here. So if I have negative 4 is the solution, and I'm dividing into 3 plus 4 minus 5 plus 3. Those are the coefficients, aren't they? So if I do my synthetic division, bring down my 3, that becomes a negative 12. Combine those, I get a negative 8. Do the multiply, I get a positive 32 minus 5 is a 27 times 4. 27 times 27 is 54 times 2 is 108. And that's a negative 108. And 3 from 108 is 105, which is the remainder. So when I take my x evaluated at negative 4, which is here, the solution, and divide it into these coefficients, I get a remainder of 105, which is what I got when I evaluated at 105, which shows me then that this is essentially a remainder of solving the equation with using a factor of x plus 4. X equals negative 4 is a solution. X plus 4 would be a factor of the above equation. Okay, so we're using both long division and synthetic division to step through processes where we can find the remainder theorem says, here's the remainder I get when I do synthetic division, and that happens to be what the value is of the function evaluated at that location, in this case, negative 4. That's what we're doing with the remainder theorem. Okay. Let's see, it's 10:02. Let me stop on that section right now and take us into the next section and make sure we get everything covered here today. And then I'll stay after for any questions you might have. So let's stop there. Let's put this material away and bring up 2.5, which looks at zeros of polynomial functions. So here we're looking at finding, let me bring out a piece of paper here for some of the objectives. we want to see if we can use the rational zero theorem to find possible zeros, which could also be called roots, which could also be called solutions. Because anytime we have a function that, depending on what it looks like, if it crosses the x-axis here or here or here, these are the zeros, right? That's where the function f of x crosses the x-axis. It crosses it here, here, and here. We'd say these are the zeros. We could also call those the roots. We could also call those the solutions. Those are the different names for the same concept. So we want to be able to find the zeros. We want to see if we can use the linear factorization theorem to find to find polynomials with the given zeros. So the linear factorization theorem says, hey, I might be given the zeros of a function, and I'm looking to find what the function looks like. And Descartes' rule of signs, we want to take a look at what that is and how we can use it. So these concepts apply to functions of the form if I have something that is some function that looks like, in general, some leading coefficient with some subscript and whatever that value is, some number, x to the n exponent. So here's a subscript, here's the same value as an exponent. Maybe that's x cubed, and or a sub 3 x cubed plus a sub n minus 1 x to the n minus 1. We just reduce it, plus, and we'll just keep going down here until we get a to the 2 x to the 2 plus a to the 1 x to the 1 plus a to the 0 x to the 0, which is just 1, isn't it? So we're talking about, in general, if we have polynomials that look like that, if we have that, then this is an if then situation. If we have that, then the factors of A0, so whatever A0 is, if I have factors that are listed, and we'll just call those factors P, and if I have factors of the leading coefficient, and if I call those Q. So these are factors of the constant term, and these are factors of the leading coefficient here. Then, and this is what the rational zero theorem turns out to be, then P divided by Q, these factors over these factors, will list all possible rational zeros or solutions or roots. So here we have a technique that was invented by Descartes, René Descartes, and he lived from 1596 to 1650, so hundreds of years ago. He came up with this, French mathematician, and he said, hey, if I've got factors of this guy and factors of this guy, and I divide the factors here, well, by the factors here, I'm going to list all possible, not to say all the solutions, every one of these are solutions, but the solutions are listed in this group, which is kind of interesting. So let's take a look at some examples. If we're given, and then I think it'll cement this a little bit better. If I'm given, let's say 4x to the 5th plus 12x to the 4th minus x minus 3. Maybe that's my polynomial, f of x. That's what the polynomial looks like. And here's my constant. So I'm going to call the factors of this p. Well, what are the factors of 3? Well, 1 and 3, those are factors, aren't they? And I will list them. Actually, I'll list them from left to right here, 1 to 3. Okay, and it turns out they can be positive or negative, can't they? So we've got plus or minus 1 and plus or minus 3. Those are the factors of 3. Those are the values we're calling p. And then over here for q, we're listing the factors of 4. Well, let's see, 1 and 4 multiply to get a 4. So those are factors. 2 and 2 multiply to 4. So our factors are 1, 2, and 4. So we'll call those q. And so the theorem says, if that's true, that's this, then p over q, well, p over q, well, p is plus or minus 1 and plus or minus 3 over q, which is plus or minus 1, plus or minus 2, plus or minus 4. So this lists all the possible factors. So then if I take 1 over 1 here, I've got plus or minus 1, that's this. 3 over 1, so plus or minus 3. 1 over 2, so that's plus or minus a half. And 3 over, let's see, I had 1 over 1, 3 over 1, 1 over 2, 3 over 2, and that's plus or minus. And then 1 over 4 and 3 over 4. So we're taking each of these top terms, the numerator, over each of the bottom terms, the denominator. So 1 over 1, 3 over 1, 1 over 2, 3 over 2, 1 over 4, 3 over 4. So what we're showing here then are all the possible rational zeros. This is all possible based on the work done by René Descartes. He's saying, hey, I've done some experiments and I've determined that this is true. So if it is true, then these are all that are possible. But then we have to determine which are the actuals, that is to say, which really are the zeros. That is to say, which ones work. And the only way we're going to find that out is to do the division. And so let's try one or two of them in a division problem. So let's just see what it looks like. Let's see what time do we have here. A couple minutes before we take our break. So let's just try, -1. Here's our first solution here, -1. So if we divide, and we'll test them synthetically. Synthetic division. And what are we looking for when we do synthetic division? If this in fact is a 0, we have no remainder, right? If this is a solution, we have no remainder. So let's just try one. Let's divide -1 into this thing. So we've got 4 x to the 5th, and we've got 12x to the 4, 0x to the 3, 0x to the 2, 1x, and a negative 3. So that's the division process that we would go through. So if we divide this here, bring down the 4, negative 4, positive 8, negative 8, negative 8, positive 8, positive 8, negative 8, negative 9, and positive 9, and positive 6. So we have a remainder of 6. So is x equal negative 1 a 0? Anyone? New volunteer before we take our break?
No, because there's a remainder.
No, because there's a remainder. Very good. Okay. No, because there's a remainder. Okay. In order for that to be a 0, we can't have a remainder. That is to say, you know, if the function looks like that, and at x equals negative 1, say here's negative 1, we ended up with a remainder of well, let's say here's negative 1. Let's say this is negative 1. And we ended up with a remainder of positive 6 at negative 1. Here's x, here's y. Then this isn't a 0, is it? The function zeros are where the function crosses the x-axis here. So if we go to some location and find out the value of the function is not 0, then we'd have a remainder. Okay, make sense to everybody? Questions on that before we take our break? Now, is a 5-minute break enough? That'll get us out at 5:05 instead of 5:10.
Yes.
All right, let's do that. So we'll see you in 5 minutes. Good work, everybody. Okay, we're back. Are there any questions that came up during the break at all? Okay. Well, if there are some, just let me know. Let's see here. See if we can find another example. Yes, here's one that I want you to be comfortable with. Let's say that you're asked to find the function, and it's of the form where it's factored. Let's say it's a sub n times, let's say x minus some value. Let's call it C1, x minus C2, x minus C3. And we are looking for a third degree. Find a third degree. Degree is exponent, right? So we want to find a cubic with real coefficients that has zeros. Let's say with zeros at x equals -3 and x equals plus or minus I. Let's say those are where we have zeros, and such that f evaluated at 8 equals, no, f evaluated, let's say f evaluated at 1 equals 8. Okay, if that's the case, the idea here is that we're looking for this value, this coefficient, because we know that f evaluated at 1 is 8. So we know what that value is, and we know that we have solutions at this value here and plus or minus this. So I've got 3 different solutions here, -3 and plus or minus I. So I'm going to say that's what these values are here. So if x minus 3 is a solution, then a factor would be x plus 3, wouldn't it? And here a factor would be x plus I and x minus I. Okay, so that's what we're plugging in up here. So keep in mind that if you're given zeros, you're given solutions, aren't you? Or roots. Roots, solutions, zeros are all the same thing, and they look like this. X equals something. That's a solution at x equals -3. Okay, so what we're going to do then is plug in what we know. So we know that f evaluated at 1 is 8. So I'm going to say f evaluated at 1 is 8. And that equals a sub n. And I'm just going to highlight that just to make sure we know what we're looking for here. This is what we're trying to find, this a sub n value, this coefficient. And we're going to multiply that times the original x minus the c value. And if the c value is -3, then we're going to say -3. That would be, this would be the factor. Here's the solution. Here's the factor. And here we have x, and then well, let's say plus I and x minus I. So let's see, we've got this value, we know that, we know we're looking for this. We know that f evaluated at 1. Well, when f evaluated at 1, that's x equals 1, isn't it? So that's what goes in these values here. So here the problem is listed such that we're trying to find this leading coefficient, and we fill in all the other values. So we'll say 8 equals a sub n times. Now, this f is 8 when x is 1. So I'm going to say 1 minus a minus 3. 1 plus I, 1 minus I. So these ones here are is this one here. Okay, so 8 equals a sub n, and that's the value we're trying to find. 1 minus a minus 3, that's a 4, isn't it? And 1 plus I times 1 minus I. And we can do the multiply and figure that out. If we can FOIL that, first times first is 1. Outer is negative I. Inner is positive I. Those cancel. And last is negative I squared. Well, I squared is negative 1, isn't it? Because I equals the root of negative 1. I squared is negative 1. So this is negative 1 times negative 1. Well, that's a 2, isn't it? So 8 equals a sub n times 4. And this is negative 1, so that makes this a 2. So that's 8 a sub n. A sub n equals 1. Okay, divide through by 8. All right, so what that tells us then is that our f of x above this a sub n value is 1. Okay, so equals, so it's just going to be whatever these coefficients are. So here it's going to be x plus 3. So it's going to be x plus 3. We're looking right here. X plus 3. We see that here, and we see that here. Times x plus 1, excuse me, x plus I, x minus I. So if we FOIL that, x times x, that's x squared. X plus I, x minus I, those cancel. And then minus I squared when we FOIL this. So that's x plus 3 times, so this, if we factor this, well, that is to say, if we simplify this, x squared minus I squared is negative 1, negative times negative is a positive. So that's going to give us a positive 1. So this tells us the function then with these values used, solutions at negative 3 plus or minus I, and f evaluated at 1 is 8. What we don't know is the a sub n. We've plugged in these values, and we get a sub n equals 1. I'll just highlight that. A sub n equals 1. So that says we have a leading coefficient of 1 that would go here, so we can just leave that out. And we end up, after we simplify, of x plus 3 times x squared plus 1. And you could also then multiply these together. F of x equals first times first. That's x cubed. X times that is x. 3 times this is plus 3x squared plus 3. Or f of x equals x cubed plus, putting them in descending order, 3x squared plus x plus 3. So our simplified answer then, after we've gone through the process, is the f of x value that we're looking for up here. We plugged in the values that we were given, solved for a sub n. Here's a sub n, and it turned out to be 1. We did it by plugging in the values. So it equals this, and then when we simplify, we end up with f of x equals x cubed plus 3x squared plus x plus 3. Okay, I'm going to stop at that point and ask for any questions on what we did there. And again, you'll have you'll have problems in the homework that'll step you through something like this. So if this is the first time you've seen it, you'll have other examples where you'll be able to step through and work the problems. Okay. If there aren't any questions at that point, I'm going to go to the next section. And I'll just gather my material here. And I'll ask one more time, are we okay with what we've done here? And I'll clip this all together. Put it over there. And the last section we're going to cover today is section 2.6, which is rational functions and their graphs. And the interesting thing here is we're going to see some graphs. Let me put out what our objectives are here. Okay, we want to be able to find the domain. Of some rational functions. And we're going to use something called arrow notation. And we're going to identify asymptotes. Both vertical and horizontal. And we're going to do some transformations. Remember, transformations, if I have a graph that looks like that, and I want to move it horizontally and vertically, I might have something that maybe got shifted to here, where this vertex here got moved from the origin of X and Y to up here, over and up. So we shifted right, we shifted up. So those are what we're calling transformation. We move from here to here. We want to be able to graph these functions. And we want to be able to identify, I'll just put ID, something called a slant asymptote. Okay, so those are the objectives of this section. And now we'll see if we can go through some example problems. Let's see here. Let me find one that looks kind of interesting here. If I have, let me take this one. If I have f of x, and that equals something that looks like this. Let's say it's x squared minus 9 over x minus 3. And I ask you to find the domain. Okay, so if we're looking for the domain, D, well, we're saying what are the values that x can take on? Here's a arbitrary 0, and x can go positive that way and negative this way. And we realize that we have a denominator here that has x minus 3, and we know that the denominator cannot be 0, don't we? Because if it were 0, then we'd be dividing by, excuse me, x can't be 3 because our denominator would force our denominator to go to 0. We can't divide by 0. Okay, so we would say then if we're looking for our domain, the way I would like you to write it is that here we have x equals 3 right here. Let's call that 3. And we can't have an x equals 3. So we could say our domain goes from negative infinity to negative 3. Doesn't include the negative infinity. Doesn't include this 3.
You would say to +3, wouldn't you, Professor? Not negative 3.
Yeah, yes, you're right. Thank you. So we doesn't include this positive 3. Or, and remember this u is the or it goes from positive 3 to positive infinity. Okay, so if we were to list our domain, then we would list it in that fashion. Okay, does that make sense to everybody? Okay, if I give you something that says g of x equals x over x squared minus 9. And you'd say, well, let's see, is there anything that would cause this denominator to go to 0? Well, let's just find out. X squared minus 9. Set that equal to 0 and find out what values of x cause that to go to 0. So x squared equals 9. X equals the root of 9 or plus or minus 3. So that says if we have a plus 3 or a minus 3, then we're not going to include those values. Because if we did include those values, that would drive this denominator to 0, wouldn't it? So now if I want to list my domain, I can do it graphically by saying, well, it looks like we can come along here, don't include that, come along here, don't include that, and go that way. So graphically, we could say, well, it sort of looks like that. We could do it using interval format, which we could say, well, we go from negative infinity to negative 3, or negative 3 to positive 3, or positive 3 to positive infinity. So that would be how we could list our domain. Okay, questions on that at all? So we've listed it, here's a graphical. Here it's interval. Remember the other notation that we could use, set notation? Remember what that looked like? We said it's a set, and we listed our set. We said, and x can be any value such that, and we could say a couple ways, I guess we could word it, but one could be x cannot be plus or minus 3. Or we could say x such that x is greater than negative infinity and less than negative 3. Or x is greater than negative 3 and less than positive 3. Or x is greater than positive 3 and less than positive infinity. So here we'd have graphical notation. Here we have interval notation. And then down here we have set notation. Okay, any questions on what we've covered there at all?
Could you explain how you found the domain again? I'm still kind of confused on that.
Okay. The domain, we're saying what are the legitimate values? What are the valid values that x can take on for this equation, for this function? In other words, can x be any value on the real number line from negative infinity to positive infinity? Can x be any of those values? We'd say, well, let's see, it can be any of those values except where x causes this denominator to go to 0. If this denominator goes to 0, we can't allow that because that says this function goes to infinity, which means we can't reach infinity. That's not a number, which says we are not allowed to divide by 0. So we're not allowed to use x equals negative 3 because if x is worth negative 3, negative 3 squared is not positive 9. Positive 9, negative 9 equals a 0. We're not allowed to divide by 0. So therefore, we're not allowed to have x be negative 3. How about positive 3? Put a positive 3, we get a positive 9. Positive 9, negative 9 is dividing by 0 again. We're not allowed to divide by 0. So we're not allowed to use a negative 3 in our solution. So graphically, it would look like this blue line. Interval format, we would look like x can be any value from negative infinity to negative 3. The parenthesis here says we don't include the 3. This parenthesis says we don't include the negative infinity. This upside, this u here indicates that that's an or value, which says it can be this or negative 3, not including negative 3, to positive 3, not including positive 3, or positive 3, not including positive 3, to positive infinity, not including positive infinity. So that's our interval format. And then set notation would say the same thing in a different notation. That makes sense?
Yeah, a bit.
Okay. Now let's take on the task of see if we can find asymptotes. And we may have vertical, and we may have horizontal. Okay, so let's take a look at an example and see what we might look like. If we have f of x equals x over x squared minus 9. I say, well, let's see. Are there any values that cause this denominator to go to 0? So we can just set that equal to 0 and see if there are. X squared equals 9, x equals plus or minus 3. So this says then that at plus 3 and negative 3, this function goes to infinity. So we have a vertical asymptote here and here, and I'm just going to put that in blue so you can see it a little better. I'm going to call this x, this y, and that 0. And this says if I get out to x equals 3, I have a vertical asymptote. And let's see what x looks like if I go out that direction. So at x is 0, I get 0 over 0 minus 9. 0 over negative 9 is what? If I substitute
It's
x,
0.
it's 0, isn't it? It's right here. Okay, so if that's the case, what if x is some different value? What if x is close to negative 3, but not negative 3? Let's say it's, let's say it's negative 2. And out here we're at positive 2. So if x is negative 2, what do we have for f of x? Well, we get negative 2 over negative 2 squared is 4 minus 9. So we get negative 2 over 4 minus 9 is negative 5. So that's negative 2/5. Negative 2 over negative 5 is positive 2/5, which is in decimal form 0.4, isn't it? So it's a positive 0.4. So if I say this is 2 and that's 1, 0.4 is less than half of that. So when x is negative 2, we're up, let's say we're right here. So here's negative 2 and 0.4. How about we're at positive 2? Where are we going to be? Well, positive 2 is going to make this value positive, and this value down here is the same, isn't it? Because whether it's positive or negative 2, it's still 4. So this is positive, so now we get a negative 0.4. So over here, we're down here. And if we put other values in this table of values, we're going to end up with something, I think, that looks sort of like that. Okay. Now, what if we go on the other side? So 2, 3, maybe we go out to 4 here and 4 here. And what are we going to get? So we can put those values in. 4 And what's this -4? So we'll say -4 squared is 16 minus 9. -4 over a positive value here. So this is 7. 9 and 7 is 16. So -4/7. That's a little over a half. So if I go here -4, I'm going to be a negative value, aren't I? So I'm going to be down in here. So if we were to complete this, what we're going to find is we're going to have a curve that sort of looks like that. And over here, if we complete the table of values, we're going to have a curve that sort of looks like that. So let me put that in a different color, maybe so we can see that a little better. I haven't put in all the table of values, but there's another way we could do that. Let's see what happens if I put x divided by x squared minus 9. And what do I want my window to be? Let's say from -5 to 5. And the y goes from, I don't know, -10 to 10. And it looks like I get something that sort of looks kind of like what we're talking about here. We go from on the left side at -3, 1, 2, 3. So I'm coming down and I'm going over and down. And then over here from my vertical at 3, I'm coming down this way. And over here, I'm going down this way. Get that over there so you can see it. So we put that in our calculator. We predicted it would look like this by doing our table of values. We can confirm it by putting into the calculator and showing that depending on how we have our window, it's going to look pretty much like that. Okay, so what we've done then is we found some vertical asymptotes here. So here's vertical asymptote here and a vertical asymptote here. Okay, questions on what we did there at all? Okay, now I might have a situation where, let's say I have some function and it's equal to, let's say x plus 3 over x squared plus 9. And let me say, well, let's see, is there any value of x that would cause this denominator to go to 0? Well, let's just set the denominator equal to 0 and see if there are any values of x. So here we get x squared equals -9. Well, that's going to be interesting, isn't it? Because we take the square root of each side and we get x equals plus or minus the root of -9. Well, that's an imaginary value, isn't it? Which says there are no values of x that cause a value of 0 on the real number line. Okay, so if that's the case, then we're not going to get any vertical asymptotes. Okay, and I could also put this, I could create a table of values and solve for x's and y's, or I could substitute this into my calculator and see what that looks like. And I think we're just going to see something that kind of does that, which says there are no vertical asymptotes. Okay, why? Because there's no value of x that would cause the denominator to go to 0. Okay. Questions on that? Okay, that was vertical. Let's try horizontal. Let's see if we can find horizontal asymptotes. Let's say we're given a function such that 4x over 2x squared plus 1. And we want to say, is there a horizontal asymptote here? Well, we could plug it into our calculator and see what it looks like, but we could also do it algebraically. And algebraically says, if we're looking for horizontal asymptotes, we're looking for values as x goes to some large value. It's headed out towards positive or negative infinity. So let's say x gets some very large value. Well, if x is very large, this 1 isn't going to really make any difference, is it? If this is 1,000,000, this 1 doesn't really do much for us. Similarly, we've got 4 times x and 2 times x squared. Well, as x gets very large, if we divide through by x, that'll cancel and we'll end up with 4 over 2x as x gets large. So as x gets large, what's going to happen to this value here? As x gets very large, what happens to 4 over 2 times x?
Continuously get closer and closer to 0.
Right. It ends up, that's right. It ends up going to 0 as x gets large. So what we're saying then is this function has a horizontal asymptote at y equals 0. That's the asymptote, because this function gets closer and closer, and that's what an asymptote is. We're going to say this function gets closer and closer to it, never reaches it. Just like here, these functions never reach the vertical asymptote. They get closer and closer, but they never reach it. Similarly here for the horizontal asymptote, y equals 0, here's x, here's y. At y equals 0, that's the x-axis, isn't it? So this function gets closer and closer to the x-axis, but never really reaches it. Okay, and again, we can look at this and say, you know, we don't even have to graph this or put in our calculator or create a table of values, because we can see that as x gets large, that doesn't make any difference. And if the x squared will always be larger than the x increasingly as x gets very large. So that's going to drive this value asymptotically close to y equals 0, or the x-axis. Okay, now let's take a look at another situation. Let's say we have some value where we have 4x squared over, let's say, 2x squared plus 1. And we say, do we have a horizontal asymptote? If so, where is it? And we'd say, well, what happens when x gets large? Well, when x gets large, that's not going to mean much. When x gets large, well, these will all get large, but these are going to cancel. So we end up with, as x gets very large, we end up with 4 over 2, which is just 2, which says then as x gets very large, then the horizontal asymptote is going to be at 2, y equals 2. And that's our horizontal asymptote right here. Okay. Questions on what we did there at all? Let's say we have f of x equals 4x cubed over 2x squared plus 1. And again, we're looking for horizontal asymptote. Say, well, what happens when x gets large? Well, when x gets large, that value is not going to mean much. And we're going to get 4 over x cubed over 2x squared. And as x gets very large, we can say x cubed divided by x squared. That's just x, isn't it? So that's 4 over 2, which is 2x. So as x gets very large, then f of x is going to look like 2x. And what do we say about a horizontal asymptote then? What's our horizontal asymptote? Anybody? New volunteer. We don't want the same people answering every question here. Ella, what do you think? Gopal, what do you think? Hudson? Junior? Anybody? Kathy? We have a horizontal asymptote, yes or no? And if so, where is it? You guys are awfully quiet out there.
It seems as if there's no asymptote.
And why is that?
Because if I try to imagine there's no horizontal line that can be drawn with that equation.
Right, because y equals 2x. So if we take a look at what that looks like, y equals 2x, well, as x gets large, it's just going to be some straight line that goes up, apparently. If it's large negative values, well, you know, it looks like it's going to go down that way then. If this is negative, it's going to be negative values. If it's positive, it goes up. And the exponent is 1. But the question was there a horizontal asymptote? It didn't ask you to graph it. It just said, where's the horizontal asymptote? And we say there is no horizontal asymptote. Okay. Makes sense on how we reasoned that out, how we got to that? Questions on how we got to that? Okay. All right, let's try this one. Let's say we have f of x. We'll call this the parent function, and we're going to do transformations. We're going to transform the function 1 over x squared. And we say, well, what does 1 over x squared look like? And we say, well, let's see here. We could create a table of values. But as x gets very large and positive, well, this as x gets very large and positive, this is going to get very small, isn't it? 1 over a large number is going to get small. So as x gets larger and larger, we're going to get closer and closer, and x gets smaller and smaller. And if it were to reach 0, well, we can't divide by 0, but if it gets very close to 0, then this number is going to get larger and larger, isn't it? So it looks like it's going to be some sort of a smooth curve that comes down like that. And similarly, if x were negative and large out here, this is still going to be a small number because negative squared is positive. So we're still here, and we're going to come up this way. All right, so we'll have our x and y axis here, and our function is going to look sort of like that. Okay. And here's our origin. So we start out with, let's say, a parent function that looks like this. And now we want to transform that. Let's say I have a g of x that shifts this function. And it looks like 1 over x minus 2 quantity square plus 1. Question is, what does this thing look like? You say, well, it looks like the parent function shifted horizontally because of this -2. And this -2 is going to shift which way, left or right?
Would it be right?
It shifts it right, doesn't it? Shifts it right 2. So this thing's going to go over 2 to the right. So it's going to go over here. And this +1 says it's going to shift it up 1, doesn't it? So here's 1. So now we have a new curve that, if I say, here's my shifted axis, here's the x and y, I now have the function that comes down here and comes down here. It's the same function, but it just moved to a new origin. Went over to the right because of the -2, and it went up 1 because of this +1 here. Okay, so g of x, which is in the y direction, goes +1, and x minus 2 shifts it in the positive direction 2. Okay, questions on what we did there? Okay, let me take you through Make sure I cover everything I want to cover here. Let me take you through the slant asymptote. Get a different equation here. Let's say, and now we're talking about let's say I'm given the function f of x equals x squared minus 4x minus 5, and I divide that by x minus 3. And I'm saying find slant asymptote. Okay, so if I were to do this long division, or synthetically, we could do it any way we want. Well, maybe we can do it both ways. If I do it long division, I'll say x minus 3 into x squared minus 4x minus 5. X goes into x squared, x times x squared minus 3x minus plus, those cancel. And I'll get x minus 5. And x goes into x one time. And this is a negative, so it goes in -1, so that's negative x, positive 3. So I'll change those, and those cancel. I'll get -8, so I get remainder equals -8. Now x x minus 1, this is the solution we get when we divide x minus 3 into this. So it turns out then that this equation here, y equals x minus 1, is the equation of the slant asymptote. So if we were to graph y equals x minus 1, if we were to graph it, here's x, here's y, -1. So when x is 0, if I create a table of values of x and y, when x is 0, y is -1, so I'm here. If x is 3, I'm at 3 minus 1 or 2. 1, 2, 3. I'm here. And if I'm at -3, I'm at -4. This was -1, 2, 3, 4. So I'm down here. So it looks like I've got a line that kind of goes like that from 3 and 2. That's that point. Here's 2. Here's -3. Here's +3. -4. This was at point 0, -1. And this is at point -3, -4. So my points are here, here, and here. My locations are here, here, and here. And my slant asymptote looks like that on my XY coordinate plane. So we started with this function, and we ended up saying the slant asymptote is here. Now let me just try an experiment here and see what I get when I put this into my calculator here. So let me put in the numerator, I'm going to put x squared minus 4x minus 5. Hope this doesn't blow up on me. And x minus 3 in the denominator. And what kind of oh, I don't know. Let's see. For a window, oh, I don't know. From, I don't know, -3 to, I don't know, 5. Maybe I should just make them equal here. -4 to 4. And y, let's say, what do we want y to be? Well, let's just say negative 10 to 10. Let's just see what it looks like here. So we've entered this value into our calculator. And we're using a window of from x goes to -4 to +4 and y goes to -10 to +10. And if I graph it, I get something that looks like that. So it looks like I want to shift my window to the right. So I'm going to say 1, 2, 3, 4. Let's say we go out here to 10. Okay, now when I go out to 10, I get a curve that looks like this. That's interesting. And then if I put my slant asymptote in there, let's see here. What did I say the slant asymptote is? Let's put that down here at x minus 1 and graph that. So here's my slant asymptote at x minus 1. And here's my function, x squared minus 4x minus 5. And you'll notice that we have an asymptote to the left and an asymptote to the right. Okay, which is, that's what we were predicting. As we said down here, we have a slant asymptote shown here. And when we actually graph it, we ended up with this value here. Okay, questions on that at all? What we did there? Okay. Let's try a new problem. Let's say, here we go. We've got some room on this side. Let's say you're given, you want to find the average cost. Find average cost. And you're given let's say average cost as a function of the number of units that you're building. And let's say the cost is a fixed cost plus a cost per unit, which I'll call variable cost. And maybe you have plant and equipment and whatever, and this value is very large. Maybe you've got $1 million worth of plant and equipment. And it turns out that the unit you're building, because of, I don't know, maybe labor costs and materials and what have you, maybe it cost you $5,000 per unit. And you're building, let's say, X units. So now your cost as a function of the number of units is going to be this fixed cost. If you build 0 units, you've still got plant and equipment that you've invested in. And variable costs might be the labor costs and materials that you have, maybe even utilities would factor in there. So that's your total cost. But if you wanted average cost per unit, then you would have to divide the total cost by the number of units you're building, wouldn't you? So you'd say, well, the average cost then is the number of units I'm going to build divided by the number of units. So we can see that if the number of units divided were 0, well, we can't divide by 0. So that wouldn't work. We can't build 0 units on this model. But if we built 1 unit, if x equals 1, so the cost of 1 unit would be 1 million plus 5,000 divided by 1, or 1 million and 5,000. And that's the average cost of 1 unit. And you're going to say, well, that doesn't work. I can't make any money selling units for $1,005,000. That doesn't work. So let's see what it goes to if I build more units than that. Well, let's say I build 1,000 units. So then my cost per 1,000 units is 1 million plus 5,000 times 1,000. So that's 1 million. plus what do we have here? 5 and what? Another 5 million. Let's see, 5,000 times 1,000. Yeah, that's another 5 million, isn't it? Okay, and then we're going to divide that by the number that we're building. How many are we building? We're building 1,000. Okay, that's this value. So now the average cost for 1,000 units is 1 million plus 5 million. That's 6 million divided by 1,000. So now my average cost is 6,000 if I'm building 1,000 units. So I'll build 1 unit, average cost is very high, can't make any money on that. If I build 1,000 units, it's 6,000. And what I'm looking for is there some value that's going to be the minimum value, no matter how many I build, I really am not going to get below whatever that value is. Well, let's make this value very large then. Say what do we want the cost of, what if we want the cost of 1 million units? Some large number. So that would be 1 million plus 5,000 times 1 million over 1 million. So that's going to be 1 million plus 5 million. That's going to be 6 million. 6 divided by 1 million. So that's going to be 6,000.
Professor, not that it really matters, but didn't you say that it was going to be 5,000 times 1 million?
Yes.
It
Yes.
should be, what, 50 billion or something?
Well, let's see. Yeah, let's do that. Let's make this realistic. Let's just go ahead and do it. So we've got 1 million here, 10 to the 6 plus, what do I get when I take 5,000 times? So that's going to be 1, 2, yeah, that's going to be a big number. 5, 0, 0, 0, 0, 0, 0, 3, 6, 9, 3, 6, 9 over 1 million. So now we've got, well, it looks like this number is going to be the defining factor, isn't it? We've got 5 billion, take out 6 zeros, 3, 6. So we can see that what we're coming up on as this number gets larger and larger, it's this value that we're reaching asymptotically. The point of this exercise is to say that we're really not going to get below 5,000. We can come down and get close to it. But as this value out here, the number of units gets very large because it's 5,000 times that very large number divided by that very large number. This number here is going to be insignificant as this gets larger and larger and larger. So we're coming down asymptotically to a value of 5,000, which says that that's the lowest average cost and the best average cost we're ever going to be able to reach. Okay, so it's up to us then to determine, well, with our plant and equipment, with our current labor costs and materials costs, utilities costs, and so forth, is this a profitable venture? That is to say, can we make money if we make a large number of these things and our lowest average cost is 5,000? If it costs us more than that, we really aren't doing anything. So we're saying then the horizontal asymptote for large numbers of values is going to be at 5,000. That's really all we're trying to look at there. Okay, we've got, what, a few more minutes. Let me take you through one more example, since we've got a little time here. Let's say that the commuter, you're a commuter and you're driving 40 miles. Now this is a problem where you may remember these problems. Distance equals rate times time. If you're going 50 miles per hour and you drive for 1 hour, then your distance is 50 miles. Unit analysis says we get miles divided by hours times hours, which gives us miles. So this distance is in miles. And if you drive, let's say 40 miles, say this distance is 40, and you drive over and back, and you're going 40 miles. But it turns out that your return trip, so let's say on this direction, distance equals rate times time. And on the return trip, distance equals rate. So that's rate 1, and let's call this rate 2 times time. And let's say that rate 2 is rate 1, but it's 30 miles per hour faster. For some reason, you're able to go faster on the return trip. Maybe it's downhill. Maybe you're on your bike and it's downhill, or whatever the issue is. But you're able to return at a faster rate. And the question is, can you express the total time to complete the trip as a function of the outgoing rate, the outgoing velocity? And the way we would attack a problem like this, distance equals rate times time, is that we would say that the distance, which is 40, equals, let's say the rate out is R1 times T. And the return trip would be distance equals, and here the rate back is R1 plus 30. And I guess I don't need the R, I could just, the subscript, I guess I could just say that's R out, and that's R back, and that's times time. And we're looking to express the time as a function of the rate that you initially started at. So we can solve each of these. We can say, well, the total time is the time that we're going out, which is to the right, plus the time that we're returning, which would be to the left. And so the time going out, which is this time, so let's solve for that. So T equals 40 over R. That's this value when we solve for T, plus this time, which is 40 over R plus 30. So now we have time out plus time in. Now we have the total time, T total, as a function of time out plus time back. So 40 over R plus 40 over R plus 30 would be the way we would put that total time as a function of the outgoing time and return time. Okay, that makes sense to everybody, what we're doing there? Okay, questions on that at all? All right, I've got 5:09, close to 5:10. I'll stay online for a minute or two here if you've got any questions. Other than that, when am I going to see you next?
We'll see you Wednesday, Professor.
Wednesday. Very good. All right.
Thank you for the lecture. You have a nice day.
Thank you, guys. You too.